Good evening, everyone, and welcome to the Droning Professor. Tonight we're going to learn about the formation of the cosmic web. So, as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. I hope you're all comfortable, because we're about to embark on a journey through the largest structures in the universe, and I promise you, it's going to be absolutely mind-bending. Today we're talking about the cosmic web, which, despite what the name might suggest, was not spun by an incredibly ambitious spider. Although, given the scale we're dealing with, that would have to be one seriously impressive arachnid. So, what exactly is the cosmic web? Imagine for a moment that you could zoom out from Earth, past our solar system, past our Milky Way galaxy, past our local group of galaxies, and keep going until you could see billions of galaxies all at once. What you'd see would look remarkably like, well, a web. Not a perfect spider web, mind you, but more like what happens when you let that spider have a few too many espressos. You'd see vast filaments of galaxies stretching across hundreds of millions of light years, intersecting at massive nodes with enormous empty voids in between. This is the cosmic web, and it's the largest known structure in the universe. It's basically the universe's scaffolding, the framework upon which everything else hangs. Now, before we dive into how this magnificent structure formed, we need to address the obvious question that I know is bouncing around in your heads. How do we even know this thing exists? It's not like we can just step outside and look up at the night sky and go, oh yeah, there's the cosmic web, right between the Big Dipper and Orion's belt. The cosmic web is far too large and diffuse to see with the naked eye, or even with most telescopes looking at small patches of sky. We discovered it through decades of painstaking work, mapping the positions of millions of galaxies across vast stretches of the universe. In the 1970s and 1980s, astronomers started conducting large-scale galaxy surveys, essentially creating three-dimensional maps of where galaxies are located in space. And what they found was shocking. Galaxies weren't distributed randomly throughout the universe like sprinkles on a cupcake. Instead, they were organized into these long, thread-like structures, walls, and clusters, with huge empty regions in between. The first hint of this large-scale structure came from the CFA Redshift survey, which began in 1977. When astronomers started plotting the positions of galaxies, they found something that looked suspiciously like structure on enormous scales. Then, in 1989, Margaret Geller and John Huchra announced the discovery of what they called the Great Wall, a massive sheet of galaxies stretching across 500 million light-years of space. That's 5 followed by 23 zeros in kilometers if you're keeping track, which I recommend you don't because you'll hurt yourself trying to visualize it. Since then, we've discovered even larger structures, like the Sloan Great Wall, which is about 1.37 billion light-years long. To put that in perspective, light from one end of this structure, traveling at 300,000 kilometers per second, would take over 1 billion years to reach the other end. And light doesn't exactly dawdle. But here's the really fascinating part. The cosmic web isn't just about where galaxies are, it's also about where they aren't. Between these filaments and walls are vast, empty regions called cosmic voids, some of which are hundreds of millions of light-years across. These voids contain very few galaxies, almost like cosmic deserts. In fact, if you were floating in the middle of one of these voids, you might see absolutely nothing in most directions. No stars, no galaxies, just darkness. It would be simultaneously the most peaceful and most terrifying camping trip imaginable. No light pollution, but also, no anything. Now that we've established what the cosmic web is, let's talk about how it got there, which is really the meat and potatoes of today's lesson. Or should I say, the dark matter and baryons. You'll get that joke in a few minutes, I promise. The formation of the cosmic web is fundamentally a story about gravity and time, with a special guest appearance by the most mysterious substance in the universe, dark matter. It's a tale that spans 13.8 billion years, from just after the Big Bang to the present day. Let's rewind to the very beginning, or at least as close to it as we can get without our physics completely breaking down. About 13.8 billion years ago, the universe began in what we affectionately call the Big Bang. Now, despite what the name suggests, it wasn't actually an explosion in space. It was an expansion of space itself. Imagine the universe as the surface of a balloon, and someone starts inflating it. Every point on the balloon moves away from every other point, not because they're moving through the surface, but because the surface itself is expanding. That's essentially what happened, except in 3 dimensions instead of 2, and without the balloon part, and also without anyone to blow it up. Okay, maybe it's not the perfect analogy, but work with me here. In the first moments after the Big Bang, the universe was incredibly hot, incredibly dense, and incredibly uniform. And when I say incredibly uniform, I mean really, really smooth. If you could have measured the density of matter and energy at different points in the early universe, you would have found it was almost exactly the same everywhere, to within about 1 part in 100,000. That's like taking 2 buckets of water, each containing exactly 100,000 molecules, and finding that one has 100,000 molecules and the other has 99,999. They're almost identical, but here's the critical point. Almost identical is not completely identical. There were tiny, minuscule variations in density from place to place. In some regions, there was slightly more matter than average. In others, slightly less. These variations were incredibly small, about 1 part in 100,000 as I mentioned, but they were there. And these tiny density fluctuations, these little seeds of imperfection in an otherwise smooth universe, are what eventually grew into the cosmic web we see today. In fact, without these initial fluctuations, we wouldn't be here. The universe would have remained a thin, uniform soup of particles, never forming stars, galaxies, planets, or professors to talk about them. Where did these fluctuations come from? This is where things get really wild. Most cosmologists believe they originated during a period called cosmic inflation, which occurred in the first tiny fraction of a second after the Big Bang. And when I say tiny fraction, I mean really tiny. We're talking about the period from about 10 to the negative 36 seconds to about 10 to the negative 32 seconds after the Big Bang. For those of you who don't speak scientific notation, that's 0.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 exponentially, growing by a factor of at least 10 to the 26, or about 100 million trillion times. Imagine if you inflated a grape to the size of the Milky Way galaxy in less than a blink of an eye. Actually, in far less than a blink of an eye, because a blink takes about 100 to 400 milliseconds. And we're talking about something that happened in 10 to the negative 32 seconds, which is about 10 to the 29 times faster than a blink. Your mind might be melting right now, and that's okay. That's a perfectly normal response to inflation. During this inflationary period, quantum fluctuations, the random jitters of particles and fields at the quantum level, got stretched out to cosmic scales. Think of it like taking a piece of fabric with a barely visible texture and stretching it until that texture becomes visible to the naked eye. These quantum fluctuations became the density fluctuations that seeded all the structure in the universe. So, in a very real sense, the largest structures in the universe have their origins in the smallest possible scales. The cosmic web started as a quantum burp that got inflated to galactic proportions. Physics is weird, folks. Now, after inflation ended, the universe continued to expand, but at a much more sedate pace. The temperature started to drop as space stretched out. For the first few 100,000 years, the universe was still far too hot for atoms to form. It was a dense plasma of particles, protons, neutrons, electrons, and photons, all bouncing off each other in a cosmic mosh pit. Light couldn't travel very far in this plasma because it would immediately scatter off the free electrons. The universe was opaque, like trying to see through a thick fog. But here's where dark matter enters our story, and it's going to be a major player. Dark matter is stuff that doesn't interact with light at all. It doesn't emit it, doesn't absorb it, doesn't reflect it. It's completely invisible to telescopes. We only know it exists because of its gravitational effects. And there's a lot of it. About 85% of all matter in the universe is dark matter. Only 15% is the ordinary matter that makes up stars, planets, and everything we can see. For every kilogram of normal matter, there's about 5.7 kilograms of dark matter lurking invisibly nearby. It's like finding out that for every person you can see, there are 6 invisible people standing around that you just can't detect. Unsettling, right? Dark matter played a crucial role in the formation of the cosmic web because it had a head start. Remember how I said the early universe was an opaque plasma? That mattered for ordinary matter, which was coupled to the photons and couldn't start clumping together effectively. But dark matter didn't care about any of that. Since it doesn't interact with light, it was free to start responding to gravity immediately. Those tiny overdense regions I mentioned, the ones that were slightly more dense than average, started pulling in more dark matter through gravity. And as they pulled in more dark matter, they became even more dense, which made their gravity stronger, which pulled in even more matter. This is called gravitational instability, and it's a runaway process. The rich get richer, the dense get denser. While ordinary matter was still coupled to the radiation and bouncing around, dark matter was quietly building up the gravitational scaffolding of the cosmic web. Think of dark matter as the construction crew that comes in first to build the frame of a house, while ordinary matter shows up later to add the walls, roof, and interior decoration. By the time ordinary matter was free to start clumping, the dark matter had already laid out the basic architecture. This brings us to an important moment in cosmic history, recombination. About 380,000 years after the Big Bang, the universe had cooled down enough that electrons could finally combine with protons to form neutral hydrogen atoms. This process is called recombination, even though, and this is hilarious to me, it was actually the first time they had combined. Physicists named it recombination because it's the same process that happens when electrons and ions recombine in a plasma, but they forgot that in the early universe, this was the first time it was happening. So we're stuck calling the first combination a recombination. Science is full of these little linguistic quirks that make me giggle. When recombination happened, the universe suddenly became transparent. Photons could now travel freely without constantly scattering off electrons. The light from this moment has been traveling through space ever since, and we can still detect it today as the cosmic microwave background radiation, or CMB. It's like the universe's baby picture, showing us what things looked like when the universe was just a toddler, cosmically speaking. And here's the beautiful part. When we map the CMB, we can see those tiny density fluctuations, the seeds of structure, imprinted as slightly warmer and cooler spots. The warmer spots correspond to slightly denser regions, and the cooler spots to slightly less dense regions. These are the baby versions of the filaments and voids we see today. After recombination, ordinary matter was finally free to fall into the gravitational wells that dark matter had been building. This is when things really started to get interesting. The slightly overdense regions, now enhanced by dark matter, started pulling in ordinary matter. As matter fell into these regions, it released gravitational potential energy, which heated it up. This process continued for millions of years, with matter flowing along the gravitational field lines from underdense regions toward overdense regions. Because of the particular pattern of the initial density fluctuations, matter didn't just collapse into spherical blobs. Instead, it collapsed first along one dimension, forming sheets or walls, then along a second dimension, forming filaments, and finally into nodes where filaments intersect. This hierarchical collapse is a key feature of cosmic web formation. Small structures formed first, then gradually merged and accreted into larger structures over time. It's called hierarchical structure formation, and it's like watching a cosmic game of Tetris being played in reverse, where small pieces combine to make bigger and bigger structures. In the denser regions along filaments and at nodes, the gravitational pull was strong enough that matter collapsed further, eventually becoming dense enough to form the first stars and galaxies. The first stars likely formed between 100 million and 200 million years after the Big Bang, in the densest peaks of the dark matter distribution. Let me paint you a picture of what was happening in different regions of the developing cosmic web. In the dense nodes and along filaments, matter was being compressed and heated. Clouds of hydrogen and helium gas were collapsing under their own gravity, fragmenting into clumps that would become the first stars. These stars were very different from the Sun. They were probably massive, perhaps 50 to 100 times the mass of the Sun, composed entirely of hydrogen and helium with no heavier elements. They burned fast and hot, living only a few million years before exploding as supernovae. These explosions created the first heavy elements, carbon, oxygen, iron, and spread them into the surrounding gas, enriching it. This enriched gas would go on to form the next generation of stars, which were smaller and longer lived. Meanwhile, in the voids, very little was happening. The matter that had been there was getting pulled away toward the denser regions. The voids were literally emptying out, becoming more and more underdense over time. A void doesn't stay the same size. It grows as matter is evacuated from it. By the present day, some voids are so empty that they contain only about 1/10 the average density of matter in the universe. As stars formed and lived and died in the dense regions, galaxies began to take shape. The first galaxies were probably small, dwarf galaxies with masses of about 1 million to 10 million times the mass of the Sun. These small galaxies gradually merged together to form larger galaxies, a process that continues to this day. Our own Milky Way galaxy has grown through countless mergers over its history, and is actually in the process of merging with several smaller galaxies right now. The Sagittarius dwarf elliptical galaxy is currently being torn apart and absorbed by the Milky Way. It's galactic cannibalism in action, though it happens over hundreds of millions of years, so it's not exactly exciting to watch in real time. The filaments of the cosmic web act as highways for matter, channeling gas and galaxies toward the dense nodes. If you could watch a simulation of cosmic web formation in fast forward, you'd see matter flowing along filaments like cars on a highway system, all heading toward the big cities at the intersections. These intersections, the nodes of the cosmic web, are where we find the largest clusters of galaxies. These clusters can contain hundreds or even thousands of galaxies, all bound together by gravity. The Coma cluster, for example, contains over 1,000 identified galaxies. The combined mass of all the galaxies, gas, and dark matter in a rich cluster can be more than a quadrillion times the mass of the Sun. That's a 1 followed by 15 zeros, in case you're counting. The gas in these clusters is incredibly hot, typically tens of millions of degrees Kelvin. When matter falls into a deep gravitational well like a galaxy cluster, it speeds up, and when it crashes into other infalling matter, that kinetic energy gets converted to heat. This hot gas emits X-rays, and we can map out the distribution of hot gas in clusters by observing them with X-ray telescopes. What we find is that the X-ray emitting gas traces out the same structures as the galaxies themselves, confirming that we're seeing the same underlying dark matter distribution. Now, let's talk numbers for a moment. because the scales involved in the cosmic web are truly staggering. A typical filament might be 100 to 300 million light-years long, but only 10 to 30 million light-years wide. That's an aspect ratio of about 10 to 1, like a very long, thin noodle. Galactic strings, if you will. The density along a filament is typically 3 to 5 times the average density of the universe, while in voids it might be only 0.1 times the average density. The nodes, where filaments intersect, are the densest regions, with densities 10 to 20 times the average. The filaments themselves aren't uniform, they're lumpy, with galaxies distributed along them like beads on a string. If you could fly along a filament, you'd encounter a galaxy or group of galaxies every few million light-years. Between the galaxies is gas, mostly hydrogen, some of it neutral, some of it ionized. This intergalactic gas is remarkably hard to study directly because it's so diffuse, but we can detect it through its effect on light passing through it. When light from a distant quasar passes through the intervening gas, the hydrogen absorbs light at specific wavelengths, creating what's called the Lyman alpha forest in the quasar's spectrum. It's called a forest because when you look at the spectrum, you see a whole forest of absorption lines, each one corresponding to a cloud of hydrogen gas somewhere along the line of sight. By studying these absorption lines, we can map out the distribution of gas along the filaments. One of the most important insights from studying the cosmic web is that it's still evolving. The structure we see today is not the final form. Gravity is still pulling matter from low-density regions toward high-density regions. Voids are still expanding. Filaments are still channeling matter toward nodes. Clusters are still growing as they accrete matter from their surroundings. The cosmic web is a dynamic, evolving structure. In fact, we can use computer simulations to predict what the cosmic web will look like in the future. Billions of years from now, the nodes will be even denser, containing even more massive galaxy clusters. The voids will be even emptier. The filaments will be even more pronounced. Speaking of computer simulations, they've been absolutely crucial to our understanding of cosmic web formation. You can't exactly build a universe in a laboratory, and even if you could, you'd have to wait billions of years to see anything interesting happen. So instead, cosmologists use powerful supercomputers to simulate the evolution of the universe. These simulations start with the initial conditions, the tiny density fluctuations we observe in the cosmic microwave background, and then let gravity do its thing. They follow the evolution of billions of particles representing dark matter over billions of years of cosmic time. The first really large-scale cosmological simulations were run in the 1990s. The GIF simulations, which stands for Galaxies in Flight, and the N-body simulations from the Virgo Consortium produced stunning images of cosmic web formation. When these simulations were first shown to astronomers, there was a collective jaw-dropping moment because what came out of the simulations looked remarkably like what we were seeing in galaxy surveys. The filaments, walls, and voids emerged naturally from the initial conditions and the action of gravity. No one had to program in the cosmic web structure. It just formed on its own. This was powerful confirmation that we understood the basic physics of structure formation. Modern simulations are even more impressive. The Millennium simulation, run in 2005, followed 10 billion particles, representing dark matter in a cubic region of space over 2 billion light-years on a side. The Illustris TNG simulations, completed in 2018, include not just dark matter but also gas, star formation, and the effects of supernova explosions and supermassive black holes. These simulations can now predict not just where galaxies should be, but what they should look like, how bright they should be, what colors they should have. And when we compare these predictions to real observations, they match remarkably well. It's one of the great triumphs of modern cosmology. But here's something that's absolutely wild. In all of these simulations, dark matter does most of the work. The ordinary matter, the stuff that makes up stars and planets in us, is basically just going along for the ride, falling into the structures that dark matter has already built. If you ran a simulation with just ordinary matter and no dark matter, you wouldn't get anything like the cosmic web we observe. The structures would be much smaller and less pronounced. This is one of the main reasons we're confident that dark matter exists, even though we've never detected a dark matter particle directly. The cosmic web simply wouldn't exist in its current form without dark matter. Now, I mentioned earlier that gravity is the main force driving cosmic web formation, but there's actually another player that becomes important: dark energy. Dark energy is, if possible, even more mysterious than dark matter. It's a form of energy that permeates all of space and causes the expansion of the universe to accelerate. We discovered dark energy in 1998 by studying distant supernovae. Astronomers expected to find that the expansion of the universe was slowing down over time due to the gravitational attraction of all the matter in it. Instead, they found it was speeding up. The universe's expansion is accelerating. This was so shocking that it earned the discoverers the Nobel Prize in Physics in 2011. Dark energy makes up about 68% of the total energy content of the universe. Dark matter is about 27%, and ordinary matter is only about 5%. We're living in a universe dominated by two things we don't understand. It's humbling, really. It's like thinking you understand how your house works, and then discovering that 95% of it is built from materials you can't see or identify. How does dark energy affect cosmic web formation? Well, on small scales within galaxy clusters and filaments, it doesn't matter much. Gravity is strong enough to overcome the expansion caused by dark energy. But on the largest scales, dark energy is winning. The voids are expanding faster than gravity can pull matter back into them. This means that on very large scales, structure formation is essentially frozen. The largest structures that can form are limited by the competition between gravity trying to pull things together and dark energy pushing space apart. There's also a temporal aspect to this. As the universe expands and dark energy becomes more dominant, the growth of structure slows down. In the future, billions of years from now, structure formation will essentially stop. The cosmic web will reach a maximum size and density and then just coast along, with its components gradually drifting apart as dark energy pulls everything away from everything else. Galaxy clusters will remain bound together, but the filaments connecting them will stretch and thin, and eventually break. The cosmic web will slowly dissolve. Of course, this will take trillions of years, so we've got some time. Let me tell you about one of my favorite structures in the cosmic web, the local group filament, which is where we live. The Milky Way is part of a small group of galaxies called, with characteristic astronomical creativity, the local group. This group contains the Milky Way, the Andromeda galaxy, which is headed toward us at about 110 kilometers per second, and about 80 smaller galaxies. The local group is part of a larger structure called the Laniakea supercluster, a name which comes from Hawaiian and means immeasurable heaven, which I think is rather poetic for a bunch of astrophysicists to come up with. Laniakea is enormous, about 500 million light-years across, and containing roughly 100,000 large galaxies. All of these galaxies are, in a sense, flowing toward a common center of mass called the Great Attractor, which is located in the direction of the Centaurus constellation, about 150 million light-years away. We can't see the Great Attractor directly because it's hidden behind the disk of our own Milky Way galaxy, but we can detect its gravitational influence on nearby galaxies. There's something out there pulling on us with the mass of tens of thousands of Milky Ways. That's either really cool or really terrifying, depending on your perspective. But even Laniakea isn't the end of the story. It's just one lobe of a larger filament. Superclusters themselves are arranged in filaments and walls. It's filaments all the way up. The larger the scale you look at, the more you see the same structures repeating: filaments, walls, nodes, and voids. This self-similar structure, where patterns repeat at different scales, is a characteristic feature of structure formation driven by gravity. It's not quite fractal, but it has fractal-like properties. Let's take a moment to appreciate just how empty the voids are. The average density of matter in the universe is about 5.9 protons per cubic meter. That's incredibly sparse already. By comparison, the air you're breathing has about 10 to the 25 molecules per cubic meter, and that's mostly empty space between molecules. In a cosmic void, the density drops to about half a proton per cubic meter, or even less. You could travel for millions of light years and encounter almost nothing. If you were in a spaceship in the middle of a void, looking out the window, you would see essentially no galaxies in most directions. The nearest galaxies might be 50 or 100 million light-years away. You would be in a region of space so empty that light from the nearest galaxy would take longer to reach you than all of recorded human history. Actually, if human civilization somehow found itself in the middle of a large void, our entire understanding of cosmology would be completely different. We might not even realize there were other galaxies until we developed extremely powerful telescopes. We might think the universe was much emptier and smaller than it actually is. The cosmic web we see from our vantage point in a filament would be invisible to civilizations in voids. It makes you wonder what we might be missing from our particular cosmic neighborhood. The large-scale structure of the universe also affects our ability to see distant objects. Light traveling from distant galaxies passes through the cosmic web, and the gravitational fields of the dark matter in filaments and clusters bend that light slightly, a phenomenon called gravitational lensing. Usually this effect is very small, causing images of distant galaxies to be slightly distorted or magnified. But sometimes, when light passes near a massive cluster, the lensing can be dramatic, creating multiple images of the same background galaxy, or stretching galaxy images into arcs and rings. Gravitational lensing has become an important tool for studying both the distant universe and the distribution of dark matter in clusters and filaments. In recent years, we've even been able to detect something called the Sunyaev-Zeldovich effect, named after the two physicists who predicted it in 1969. When photons from the cosmic microwave background pass through a hot gas in a galaxy cluster, some of them get scattered by electrons in the gas, gaining a little bit of energy in the process. This causes a characteristic distortion in the CMB spectrum that we can detect. By mapping this distortion across the sky, we can find galaxy clusters and trace out the hot gas in filaments. It's another independent way to map the cosmic web, and it's particularly useful for finding distant clusters that might be too faint to see directly. Now, I want to address something that sometimes confuses students. When we talk about the expansion of the universe, we're talking about space itself expanding. Galaxies aren't moving through space away from each other, at least not primarily. Space between them is growing. Think back to that balloon analogy. As you inflate the balloon, points on the surface get farther apart, not because they're moving across the surface, but because the surface itself is stretching. This is why we can observe galaxies that are receding from us faster than the speed of light. They're not actually moving through space faster than light, which would violate relativity, but the space between us and them is expanding fast enough that the combined effect is a recession velocity greater than light speed. This expansion affects the cosmic web in interesting ways. Filaments are stretching as space expands, but the matter within them is also being pulled together by gravity. The result is a competition between expansion, trying to thin out filaments, and gravity, trying to compress them. In dense regions, gravity wins and structures continue to grow. In less dense regions, expansion wins and structures are slowly pulled apart. The boundary between these regimes is constantly shifting as dark energy becomes more dominant over time. One of the profound implications of cosmic web structure is what it tells us about the nature of dark matter. Remember, we don't know what dark matter is made of. We've never detected a dark matter particle in a laboratory, but by studying the formation and structure of the cosmic web, we can constrain its properties. For example, we know that dark matter must be cold, meaning the particles were moving slowly relative to the speed of light in the early universe. If dark matter were hot, moving at relativistic speeds, it would have smoothed out small-scale structures. We wouldn't see the lumpy, filamentary web we observe. Instead, we'd see a much smoother universe with only very large structures. The existence of galaxies and clusters tells us that dark matter has to be cold. We call the standard model of cosmology the lambda-CDM model, where lambda stands for dark energy and CDM stands for cold dark matter. We also know that dark matter can only interact through gravity, or if it interacts through other forces, those interactions must be incredibly weak. If dark matter interacted strongly with ordinary matter or with itself, it would have behaved differently in the early universe. The cosmic web is, in a sense, a giant dark matter detector, telling us about dark matter's properties through its large-scale gravitational effects. There are several candidates for what dark matter might be. The leading candidate for many years has been something called weakly interacting massive particles, or WIMPs. These are hypothetical particles that have masses somewhere between 10 and 1,000 times the mass of a proton and interact only through gravity and the weak nuclear force. Despite decades of searching with increasingly sensitive detectors, we haven't found them yet. Another candidate is the axion, a much lighter particle that was originally proposed to solve a different problem in particle physics. There are experiments underway to detect axions as well. Or dark matter could be something completely different that we haven't thought of yet. Physics is full of surprises. Whatever dark matter turns out to be, the cosmic web is its fingerprint, the large-scale signature of dark matter's gravitational influence over billions of years. When we finally identify the dark matter particle, and I'm optimistic we will eventually, the cosmic web will have played a crucial role in guiding us there. Let's talk about what happens in the densest parts of the cosmic web, the galaxy clusters at the nodes. These are among the most spectacular objects in the universe. The Coma cluster, which I mentioned earlier, has a total mass of about 10 to the 15 solar masses, most of it in the form of dark matter. The visible galaxies make up only about 2% of the total mass. The hot X-ray emitting gas makes up about 15%. The rest, about 83%, is dark matter. This ratio holds pretty much across all clusters. The visible stuff is just the tip of the iceberg. In the centers of these clusters, galaxies are packed densely together. In the Coma cluster, there are regions where galaxies are separated by only a few 100,000 light-years. That might sound like a lot, but remember that galaxies themselves are typically 100,000 light-years across, so they're only a few galaxy diameters apart. This close proximity means that galaxies and clusters can and do collide and merge with each other. When two galaxies merge, it's not like two cars crashing. The stars in each galaxy are so far apart that they almost never actually collide with each other. Instead, the galaxies pass through each other like ghosts, but their gravitational interaction tears them apart, scattering stars and triggering bursts of new star formation as gas clouds collide and compress. At the very centers of clusters, we often find the largest galaxies in the universe, brightest cluster galaxies, or BCGs. These are massive elliptical galaxies with masses of up to 1 trillion solar masses, containing trillions of stars. They form through the merger of many smaller galaxies over cosmic time. The BCG sits at the bottom of the cluster's gravitational well, and smaller galaxies spiraling inward eventually merge with it, adding their stars to the BCG's collection. It's galactic cannibalism taken to the extreme. These galaxies are so massive that their centers contain supermassive black holes, with masses of billions or even tens of billions of solar masses. The hot gas in clusters is fascinating in its own right. It's heated to tens of millions of degrees, so hot that it emits X-rays. In some clusters, the central galaxy's supermassive black hole is actively feeding, and it launches powerful jets of plasma that plow into the surrounding hot gas, creating enormous bubbles and cavities. These bubbles can be hundreds of thousands of light years across. The energy released by these active galactic nuclei helps to regulate the amount of gas that can cool and form new stars in the cluster. It's a cosmic thermostat, preventing the cluster from forming too many stars and using up all its gas too quickly. Now, let me tell you about one of the most remarkable aspects of cosmic web research. The fact that we can see evidence of it in our local neighborhood. The Milky Way isn't moving randomly through space. It's falling along the filament of the cosmic web toward the Virgo cluster, which is about 50 million light-years away. At the same time, we're being pulled by the Great Attractor and being pushed away from the void behind us. Our motion through space, about 600 kilometers per second, relative to the cosmic microwave background, is the combined effect of all these gravitational influences. We're surfing the cosmic web. You can even see evidence of cosmic web structure in your backyard, sort of. Not directly, obviously, but the distribution of galaxies visible to amateur telescopes shows patterns. The Virgo cluster is prominent in spring skies in the northern hemisphere. The Leo spur, a filament extending from the Virgo cluster, contains many bright galaxies. The Fornax cluster is visible in the southern hemisphere. These aren't random collections of galaxies, they're parts of the local cosmic web, and you can see them with a decent telescope and a dark sky. As our observational techniques have improved, we've been able to map the cosmic web in more and more detail. The Sloan Digital Sky Survey, which began in the year 2000, has mapped the positions and distances of millions of galaxies. The resulting three-dimensional maps are breathtaking. You can see the filaments and voids with stunning clarity. More recently, spectroscopic surveys like BOSS, the Baryon Oscillation Spectroscopic Survey, and eBOSS have pushed these maps to even larger distances, mapping the cosmic web as it existed billions of years ago when the universe was younger. By comparing the structure at different cosmic epochs, we can watch the cosmic web evolve over time. One of the things these surveys have revealed is that the cosmic web has a characteristic scale. The typical separation between filaments is about 300 to 500 million light-years. This scale is set by the physics of the early universe, specifically by something called baryon acoustic oscillations. In the first few 100,000 years after the Big Bang, before recombination, the hot plasma of the early universe was ringing like a bell. Pressure waves, essentially sound waves, were propagating through the plasma at about half the speed of light. These were caused by the competition between gravity trying to compress the plasma and radiation pressure trying to push it apart. When recombination happened and the universe became transparent, these sound waves froze in place, leaving an imprint on the distribution of matter. The distance these waves had traveled by the time of recombination, about 490 million light-years in today's expanded universe, set a preferred scale for structure formation. Matter was slightly more likely to clump at separations of this distance, which is why we see this scale reflected in the cosmic web today. The baryon acoustic oscillation scale is incredibly useful for cosmology because it acts as a standard ruler. We know how big it should be based on physics, so by measuring how big it appears at different distances, we can figure out how the universe has expanded over time. This helps us constrain the properties of dark energy and the overall geometry of the universe. It's one of the key pieces of evidence that confirm dark energy exists and that the universe is spatially flat, meaning parallel lines stay parallel forever, just like in Euclidean geometry. Speaking of the geometry of the universe, the cosmic web can only form in the way it has because the universe is very close to flat. If the universe were significantly positively curved, like the surface of a sphere, or negatively curved, like a saddle, the geometry would affect how structures grow. In a highly curved universe, the cosmic web would look quite different. The fact that we see the web structure we do is yet another piece of evidence that we live in a flat, or very nearly flat, universe. Now, I want to take a moment to talk about something that sometimes gets overlooked in discussions of cosmic structure, the role of feedback. Feedback, in the astrophysical sense, refers to processes where the formation of structures affects the surrounding environment in ways that influence future structure formation. For example, when massive stars form and explode as supernovae, they blast gas out of their host galaxies. This gas can travel for millions of light years before falling back or being incorporated into other galaxies. This process, called galactic winds, redistributes matter on large scales and can suppress star formation in smaller galaxies. Similarly, the supermassive black holes at the centers of galaxies can launch powerful jets that heat the surrounding gas, preventing it from cooling and forming new stars. This is called AGN feedback, where AGN stands for active galactic nucleus. Without AGN feedback, our simulations predict that galaxies would form far too many stars too quickly, using up all their gas in the first few billion years. The fact that we see old galaxies that still have gas and are still forming stars slowly tells us that something is regulating star formation, and AGN feedback is the leading candidate. These feedback processes affect the cosmic web because they move matter around on large scales. Gas blown out of galaxies can travel along filaments or fall into voids. The exact distribution of gas in galaxies in the cosmic web depends on the details of these feedback processes. This is one reason why modern cosmological simulations have to include not just dark matter, but also the complex physics of gas, star formation, black holes, and feedback. It's all connected. Let me tell you about one of the most ambitious projects to map the cosmic web, the ongoing DESI survey, the Dark Energy Spectroscopic Instrument. DESI started observations in 2021 and plans to measure distances to 40 million galaxies and quasars over 5 years. This will create the most detailed three-dimensional map of the cosmic web ever made, extending out to galaxies that we're seeing as they were 11 billion years ago, when the universe was only about 3 billion years old. By mapping the cosmic web at such early times, DESI will help us understand how structure formation has proceeded over most of cosmic history and will give us new insights into the nature of dark energy. There's also the upcoming Euclid mission from the European Space Agency, which launched in 2023, and the Nancy Grace Roman Space Telescope from NASA, planned for launch in the mid-2020s. These space telescopes will map the shapes and positions of billions of galaxies with unprecedented precision. By studying the subtle distortions in galaxy shapes caused by gravitational lensing from the dark matter in the cosmic web, they'll create maps of the dark matter distribution itself, not just where galaxies are, but where the dark matter that dominates the mass is located. One question that often comes up is, are we in a special place in the cosmic web? The answer is both yes and no. We're not at the center of anything. There is no center to the universe. But we are in a somewhat denser than average region, specifically in a filament. This makes sense because galaxies form in denser regions. If we found ourselves in a void, we probably wouldn't exist, because voids don't have enough matter to form many stars and planets. So, there's a selection effect. We observe the universe from a location where structure formation has been successful enough to create stars, planets, and eventually life. This is a weak form of the anthropic principle. We find ourselves where conditions are suitable for our existence. However, within filaments, our location seems pretty typical. We're not in a particularly special galaxy. The Milky Way is a fairly average spiral galaxy. We're not in a cluster, just a small group. We're not unusually close to any major structures. In that sense, we have a fairly representative view of a typical part of a cosmic filament. This is actually reassuring from a scientific perspective, because it means our observations should be representative of what observers in similar locations throughout the universe would see. Now let's talk about what the cosmic web tells us about the ultimate fate of the universe. The future evolution of the cosmic web depends critically on the nature of dark energy. If dark energy remains constant, as it appears to be, a property called a cosmological constant, then the universe will continue to expand forever at an accelerating rate. The cosmic web will gradually stretch out, with filaments thinning and eventually fragmenting. Galaxy clusters will become more and more isolated as the space between them grows. Eventually, in hundreds of billions of years, galaxies outside our local cluster will be moving away from us so fast that no light they emit will ever reach us. They'll cross the cosmic event horizon. Future astronomers trillions of years from now, if any exist, won't be able to see the cosmic web at all. They'll only see their local cluster, isolated in an otherwise dark universe. They might conclude, incorrectly, that they live in a small universe containing only a few dozen galaxies. It's a sobering thought. Future observers might not have access to the same cosmological information we do. But if dark energy is not constant, the future could be very different. If dark energy strengthens over time, a scenario called phantom dark energy, the universe's expansion could accelerate so much that it eventually tears apart even gravitationally bound structures. First, the cosmic web filaments would dissolve. Then galaxy clusters would be ripped apart. Then individual galaxies. Then solar systems. Eventually, even atoms could be torn apart in what's called the Big Rip. This is a rather unpleasant end for the universe, but current observations suggest it's unlikely. The data are consistent with a cosmological constant, which doesn't change over time. On the other hand, if dark energy weakens or even reverses, the universe's expansion could slow down and eventually reverse, leading to a big crunch where everything collapses back together. In that scenario, the cosmic web would eventually stop expanding and start contracting. Filaments would get denser, clusters would merge, and eventually everything would collapse into a hot, dense state similar to the Big Bang, but in reverse. Some theories suggest this could even lead to a cyclic universe that bounces between big bangs and big crunches indefinitely. It's cosmological Groundhog Day. Again, current evidence doesn't support this, but we can't rule it out completely. The most likely scenario, based on everything we know now, is the one I mentioned first: eternal expansion with gradually dissolving structure. The cosmic web is a temporary phenomenon, existing for perhaps 1 trillion years in a universe that could last infinitely long. We're living in the era of stars and galaxies, when the universe is interesting and complex. In the far future, it will be much emptier and simpler. We're lucky to be living in interesting times, cosmologically speaking. Let me circle back to something I mentioned earlier: the role of cosmic web structure in galaxy formation. The location of a galaxy within the cosmic web has a profound influence on its properties. Galaxies in clusters tend to be elliptical, old, red, and not forming many new stars. We call these red and dead galaxies. They've used up or lost most of their gas, and they're just coasting along with the stars they've already made. In contrast, galaxies in filaments and in the outskirts of groups, like the Milky Way, tend to be spiral galaxies that are still forming stars. They're blue, young, and actively growing. This is because galaxies in dense environments, like clusters, experience processes that remove their gas. As a galaxy moves through the hot gas in a cluster, the hot gas strips away the cool gas that would otherwise form stars, a process called ram pressure stripping. Galaxies in clusters also undergo more mergers, which can transform spiral galaxies into ellipticals. This environmental dependence of galaxy properties is one of the key predictions of the cosmic web paradigm, and it's been confirmed by observations. We can use the properties of galaxies to trace out the cosmic web structure, even in regions where we haven't mapped it directly. Blue, star-forming galaxies are signposts of filaments and lower density regions. Red, dead galaxies mark the locations of clusters. It's like being able to infer the structure of a city by looking at the types of buildings. Skyscrapers tell you you're downtown, while single-family homes indicate suburbs. There's also a phenomenon called cosmic web detachment, where galaxies can be ejected from the cosmic web structure by galaxy-galaxy interactions, or by the tidal forces in clusters. These orphan galaxies end up in voids, isolated from the rest of the cosmic web. They're fascinating objects because they evolve in complete isolation without any external influences. Studies of void galaxies have found that they tend to be small, blue, and actively forming stars, but at a slower rate than similar galaxies in filaments. They're like cosmic hermits, living alone in the wilderness. I want to spend a few minutes talking about the intergalactic medium, or IGM, the gas that fills the space between galaxies. This is actually where most of the ordinary matter in the universe is located. About 50% of the ordinary matter is in the IGM, while only about 10% is in stars, and the rest is in various forms of gas, in galaxies and clusters. The IGM is incredibly diffuse and hard to study, but it plays a crucial role in cosmic web dynamics. Gas flows through the IGM along filaments, accreting onto galaxies and fueling star formation. When you look at a simulation of cosmic web formation that includes gas, you see vast rivers of gas flowing along dark matter filaments, feeding the galaxies like cosmic irrigation systems. The IGM has a fascinating temperature structure. Most of it is warm, about 10,000 to 1,000,000 degrees Kelvin, which we call the warm-hot intergalactic medium, or WIM. This gas is hot enough to be highly ionized, but too cool to emit strong X-rays, which makes it very difficult to detect. For years, this gas was called the missing baryon problem, because when astronomers added up all the ordinary matter they could see in stars, galaxies, and hot cluster gas, they only accounted for about half of what should exist based on Big Bang nucleosynthesis calculations. The other half was missing. We now know it's in the WIM, hiding in the filaments of the cosmic web. Recent observations with X-ray satellites and ultraviolet telescopes have finally detected this gas, solving the missing baryon problem. There's a beautiful technique for mapping the IGM called the Lyman alpha forest that I mentioned earlier, and I want to go into a bit more detail about it because it's so clever. When you observe a distant quasar, its light has to pass through all the intervening gas between it and us. Neutral hydrogen in this gas absorbs light at a specific wavelength called Lyman alpha, which is 121.6 nanometers in the rest frame. But because the universe is expanding, the light gets redshifted, stretched to longer wavelengths. The amount of redshift depends on how far away the absorbing gas is. So when you look at the spectrum of a distant quasar, you see not just one absorption line, but a whole forest of them, each one corresponding to a cloud of hydrogen at a different distance along the line of sight. By analyzing this forest of absorption lines, astronomers can map out the distribution of neutral hydrogen along the filaments between us and the quasar. It's like doing cosmic archaeology, reconstructing the structure of the intervening space from the shadows it casts on the quasar's light. The Lyman alpha forest has been instrumental in mapping the cosmic web at high redshifts, showing us what the structure looked like billions of years ago. One of the remarkable findings is that the cosmic web was already well established when the universe was only about 3 billion years old. The same basic structure of filaments, walls, and voids was already in place, just less pronounced than today. This tells us that structure formation happened relatively quickly, which in turn constrains the properties of dark matter and dark energy. Let's talk about something that's on the cutting edge of cosmic web research. Using the cosmic web to test fundamental physics. The distribution of structure on large scales is sensitive to some very subtle effects. For example, if neutrinos, those ghostly particles that barely interact with anything, have mass, they would affect the growth of structure on certain scales. Neutrinos move at nearly the speed of light, so they smooth out small-scale structure. By measuring the cosmic web structure precisely, we can put limits on the sum of neutrino masses. Current data from cosmic web observations, combined with other measurements, tell us that the sum of all three neutrino masses must be less than about 0.12 electron volts. For comparison, an electron has a mass of about 511,000 electron volts, so neutrinos are at least 4 million times lighter than electrons. That's an amazingly precise constraint on a particle property derived from looking at the largest structures in the universe. It's physics across scales, from the subatomic to the cosmic. Similarly, the cosmic web can test theories of modified gravity. Some physicists have proposed alternatives to dark energy, where gravity works differently on very large scales. These modified gravity theories make different predictions about how structure should grow over time. By measuring the cosmic web structure at different epochs and comparing to predictions, we can test whether Einstein's general relativity holds on cosmic scales, or if we need a new theory of gravity. So far, general relativity keeps passing every test we throw at it, but we keep testing because, if it ever fails, that would be a revolution in physics. There's also a fascinating connection between the cosmic web and the study of cosmic magnetic fields. Filaments and clusters appear to have magnetic fields permeating them, though the origin of these fields is still somewhat mysterious. One possibility is that they were generated in the very early universe and have been amplified as structure formed. Another is that they were created by the first stars and galaxies and then spread throughout the IGM. These magnetic fields can affect how gas flows along filaments and can even affect the propagation of cosmic rays, high-energy particles that travel through space. Observations of radio emission from filaments and clusters are starting to reveal the presence of these magnetic fields, opening up a new window on cosmic web structure. Now, I want to address a common misconception. When we show images of the cosmic web from simulations or from galaxy surveys, we're not showing you everything that's there. We're showing you where galaxies or dark matter are concentrated. But between the filaments, in the voids, there's still stuff there. It's just very diffuse. If you could somehow measure the matter density everywhere in space with perfect precision, you wouldn't see sharp boundaries between filaments and voids. Instead, you'd see a smooth gradient, with density gradually decreasing as you move from filaments into voids. The boundaries we draw are somewhat arbitrary, based on where we choose to set our density threshold. This is important to keep in mind because the universe is fundamentally continuous, not divided into discrete compartments. Let me tell you about one of the most exciting recent developments in cosmic web research: direct imaging of filaments. For a long time, we could only infer the existence of filaments from the distribution of galaxies. The actual gas and dark matter in the filaments was too diffuse to image directly, but in the last few years, astronomers have managed to detect the faint glow of hydrogen gas in filaments using incredibly sensitive instruments. In 2019, a team reported detecting Lyman alpha emission from a filament connecting two quasars at high redshift. The quasars act like cosmic flashlights, illuminating the gas in the filament and making it visible. It was the first time we'd actually seen a filament glowing rather than just inferring its existence from galaxy positions. Since then, other filaments have been detected in a similar way. We're moving from indirect inference to direct observation of the cosmic web itself. There are also efforts to detect filaments through their gravitational lensing effects. Even though individual filaments aren't massive enough to create strong lensing like clusters do, the collective effect of many filaments should create a weak lensing signal. By carefully measuring the shapes of millions of background galaxies and looking for coherent distortions, astronomers are starting to detect the gravitational fingerprints of filaments. It's like seeing the cosmic web through its gravitational shadow. One thing that strikes me as particularly elegant about cosmic web formation is how it emerges from such simple initial conditions. The early universe was remarkably smooth and simple, just tiny density perturbations in a hot plasma. No complex structures, no organization, just quantum noise inflated to cosmic scales. And from this simplicity, through nothing but the action of gravity over billions of years, emerged the magnificent complexity of the cosmic web. It's a beautiful example of emergent complexity, where simple rules operating over long timescales produce intricate structures. You see similar things in biology, where simple genetic rules produce the complexity of ecosystems, or in chemistry, where simple atomic interactions produce the complexity of molecular structures. The cosmic web is physics' contribution to this pattern of emergence. This emergence also means that the cosmic web is, in a sense, predictable. Given the initial conditions and the laws of physics, we can calculate what the cosmic web should look like, and when we observe the real universe, that's what we see. This predictability is one of the great successes of modern cosmology. We've gone from a state where we didn't even know other galaxies existed, just a century ago, to being able to predict and confirm the structure of the universe on the largest scales. That's an incredible achievement of human intellect and ingenuity. But we shouldn't get too cocky. Remember, we still don't know what makes up 95% of the universe. Dark matter and dark energy remain mysterious. We don't know if the cosmic web is the largest structure, or if there are even larger patterns beyond what we can currently observe. The observable universe has a radius of about 46 billion light-years, but the actual universe could be much, much larger, possibly infinite. If it's infinite, then the cosmic web extends infinitely in all directions, with the same statistical properties everywhere. That's the cosmological principle. The universe is homogeneous and isotropic on large enough scales, but we can only test this principle out to the edges of what we can observe. There's also the question of whether our universe is the only one. Some theories in physics, particularly inflation combined with string theory, suggest that our universe might be just one bubble in an eternally inflating multiverse, where different bubbles have different physical laws. In some of these other universes, the cosmic web might not exist at all because the laws of physics are different. Or it might exist but look completely different because the initial conditions were different. This is all highly speculative, but it's a reminder that even when we understand the cosmic web in our universe, we might only be understanding one example of how universes can be structured. Let me bring us back down to Earth, or at least to our cosmic neighborhood. The Milky Way's place in the cosmic web affects us in very concrete ways. The stream of galaxies falling toward us along the filament means that we're constantly encountering new galaxies. Some of these merge with us, adding their stars to our galaxy. The Sagittarius dwarf galaxy I mentioned earlier is being torn apart right now, and over the next few billion years, its stars will be completely absorbed into the Milky Way. There are several other small galaxies that will eventually merge with us as well. In about 4 billion years, the Andromeda galaxy will collide with the Milky Way, and the two will merge into a giant elliptical galaxy that astronomers have cleverly nicknamed Milkomeda. This merger is a direct consequence of our location in the cosmic web. We're part of the same local structure, gravitationally bound together, and eventually will merge. On an even more local scale, the distribution of matter in our cosmic neighborhood affects the motion of our solar system through the galaxy. We're orbiting the galactic center at about 220 kilometers per second, taking about 230 million years to complete one orbit. But we're also bobbing up and down through the galactic disk, oscillating with a period of about 64 million years. Some researchers have speculated that these oscillations might correlate with mass extinction events on Earth, the idea being that when we pass through the dense galactic disk, we might encounter more comets or cosmic rays. This is pretty speculative and controversial, but it's an example of how our location in cosmic structure might potentially affect life on Earth, even on evolutionary timescales. As we approach the end of our time together, I want to leave you with a sense of where the field is heading. The next decade is going to be incredibly exciting for cosmic web research. The surveys I mentioned, DESI, Euclid, Roman, and others, will give us unprecedented maps of the cosmic web. We'll be able to trace its evolution from when the universe was less than 1 billion years old to the present day. We'll map the dark matter distribution with exquisite precision. We'll detect more filaments directly through their emission and lensing. We'll measure the properties of dark energy and test alternative theories of gravity. We'll constrain neutrino masses and possibly detect other exotic particles through their effects on large-scale structure. There's also the possibility of completely new discoveries. The history of astronomy is full of surprises, things we didn't expect to find. When the first galaxy surveys revealed the cosmic web in the 1980s, it was unexpected. When we discovered dark energy in 1998, it was completely shocking. Who knows what else is hiding in the cosmic web, waiting to be discovered? Maybe there are new types of dark matter interaction that only become apparent on the largest scales. Maybe there are topological defects left over from the early universe, like cosmic strings or domain walls. Maybe there are signatures of physics from before the Big Bang. The universe has surprised us before, and it will almost certainly surprise us again. One of the things I love most about studying the cosmic web is how it connects to so many other areas of astrophysics and physics. To understand cosmic web formation, you need to understand gravity, dark matter, dark energy, thermodynamics, fluid dynamics, plasma physics, nuclear physics, stellar evolution, galaxy formation, and probably a dozen other fields I'm forgetting. It's a unifying topic that brings together almost everything we know about the universe. It's also a beautiful example of how science works, building on observations, theory, simulations, and more observations in an iterative process that gradually reveals the true nature of reality. The cosmic web also gives us perspective. When you realize that our galaxy is just one of hundreds of billions of galaxies, arranged in this vast web structure spanning billions of light years, it's humbling. We're incredibly small in the cosmic scheme of things, but at the same time, we're part of it all. Every atom in your body was forged in the nuclear furnaces of stars that formed in the dense regions of the cosmic web. We're made of star stuff, as Carl Sagan famously said, but more specifically, we're made of cosmic web stuff. The atoms in your left hand might have come from a different galaxy than the atoms in your right hand, brought together by the gravitational flows along cosmic filaments. You are, quite literally, a piece of the cosmic web that has gained the ability to contemplate itself. And contemplate it we should, because the cosmic web tells us something profound about the nature of our universe. It shows us that the universe is not random or chaotic, but structured and governed by comprehensible physical laws. It shows us that complexity can emerge from simplicity, that structure can grow from near uniformity, that order can arise from disorder. These are powerful principles that apply not just in cosmology, but in many areas of science and perhaps even philosophy. The cosmic web also reminds us of how far we've come in our understanding of the universe. 100 years ago, we thought the Milky Way was the entire universe. 50 years ago, we didn't know the cosmic web existed. Today, we can simulate its formation on computers and map it across billions of light years. What will we know 50 years from now? 100 years from now? I can't wait to find out, even though I probably won't be around to see it. But some of you might be, and I hope you'll remember this lesson when you hear about the next great discovery in cosmology. Before I close, let me leave you with one final thought. The cosmic web is still forming. It's not a static structure, but a dynamic, evolving pattern. At this very moment, galaxies are flowing along filaments. Gas is accreting onto clusters. Voids are expanding. The universe is changing, albeit slowly by human standards. When you look up at the night sky, you're seeing the cosmic web in action. Every photon that hits your eye has traveled through the cosmic web structure, bent slightly by the gravitational fields of filaments and clusters, carrying information about the large-scale structure of the universe. You're part of this vast cosmic dance, and so am I, and so is everyone and everything we know. The cosmic web isn't just something out there to study. It's the context in which our existence unfolds. It's the structure of our cosmic home, and it's absolutely magnificent. Good night, everyone. Thank you for joining me on this journey through the largest structures in the universe. Keep looking up, Keep asking questions and never stop being amazed by the cosmos. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.